Mathematical algebras are bound by strict dimensional limits. When infinite combinatorial structures are forced into these finite spaces, the framework shatters. This stack represents the Hurwitz theorem and the Cayley-Dickson chain. It proves there are exactly 4 normed division algebras over the reals: one-dimensional real numbers, two-dimensional complex numbers, four-dimensional quaternions, and eight-dimensional octonions. If the dimensions double again to the 16-dimensional Sedenions, the algebra lose the division property. Sedenions are a 16-dimensional algebra where zero divisors appear, non-zero numbers that multiply to yield 0. Ramsay theory operates on complete graphs, denoted as Kn, where every node connects to every other node. The number of edges in these networks accelerates without bound. To represent a two-color assignment for a graph with only 100 vertices, we require an independent dimension for every edge. That requires an algebra with 4,950 dimensions. Encoding these combinations is impossible within any finite-dimensional algebraic framework. Theoretical physicist Carlos Martins proposed a structural solution, a mathematical space called the Infiniteon algebra, denoted as I. This algebra consists of exactly one real dimension and a countably infinite number of imaginary dimensions, known as Aleph null. The single real dimension encodes the systemic bias, or asymmetry, between the two colors in the network. The infinite imaginary dimensions correspond to the edges of an infinitely large complete graph, K infinity. Every connecting line in the infinite network is assigned its own dedicated geometric axis. The Infiniteon is a rigorously defined algebraic structure that creates a geometric home for infinite graph data. This equation defines an Infiniteon, splitting into a real scalar, r, and imaginary components, xe. Graph colors set xe to positive or negative 1. The real part, r, dictates the search criteria, translating any target-click imbalance into a measurable coordinate on the real axis. In balanced problems where both target clicks are the same size, the real part is 0. The problem remains entirely within the imaginary dimensions. Combinatorial graph properties, colorings, and structural bias are now translated into geometric coordinates. Dimensions in this space interact through a specific multiplication law called the Ramsay product. Rule R2 shows multiplying an edge dimension by itself results in -1. Under Rule R3, when adjacent edges multiply, they close the triangle, outputting the third edge. The cyclic vertex path determines its sign. Together, these rules make every triangle locally identical to quaternions. Local graphical connections are governed by predictable, non-random algebraic geometry. Rule R5, known as Ramsay Orthogonality, separates the infiniton from existing Clifford algebras. In this 4-node graph, if we multiply two edges that do not share a vertex, the product is exactly 0. They are algebraically invisible to each other. Standard Clifford algebras require non-adjacent basis pairs to yield a non-zero output. That makes them unsuitable for modeling the sparse connectivity of graphs. This zeroing effect leads to Theorem 3, the Ramsay skip. It makes the algebra strictly non-associative, meaning the order of multiplication changes the result. In the proof equation, multiplying the disjoint pair first on the left side collapses them to 0, ending the calculation. But multiplying adjacent edges first closes a triangle. That new edge shares a vertex with the third, yielding a valid non-zero output. This non-associativity at the 4-node scale is the mathematical requirement for modeling infinite graph networks. With this new framework, we can now map the discrete combinations of the infinite graph onto a continuous topological surface. This transformation is the split norm. It warps the algebra into the shape of an infinite-dimensional hyperboloid. The waist of this shape is the null-cone. It represents the boundary where the real asymmetry and the imaginary coloring variance exactly balance. Asymmetric Ramsay targets determine the specific real part coordinate needed to approach this boundary. We measure the position of the system using the Jansen order parameter, R tilde. The Jansen order parameter is a metric used in probability to track the likelihood of small subgraphs within a larger random graph. The Ramsay threshold occurs at the precise geometric moment when the system's order parameter strikes the null cone. This trajectory tracks the renormalization group flow, showing how the system changes across scales. The flow begins in a bound phase of coloring noise. As it scales, it sheds these imaginary components until the monochromatic clique crystallizes into a purely real point. This alignment demonstrates that the Infiniteon algebra defines the internal logic of Ramsay statistics theory. The Infiniteon theory provides a mathematical bridge between the discrete assignment of colors and the continuous trajectories of the renormalization group flow.